Hello everyone and welcome to lecture today. So today what we'll be discussing is what's called indeterminate forms. An indeterminate form is an expression that is not definitively or precisely defined mathematically. And there are many different examples, many different examples of indeterminate forms that show up in many different applications that are very important all over the place, in physics, in engineering, aerospace engineering, mechanical engineering, chemical engineering, just regular chemistry, more advanced chemistry, more advanced physics, right? And we'll kind of see some examples of this as we move on through the lecture. So I'll write some of these down right here so you get an idea of what these things are going to look like. The two most important indeterminate forms are 0 over 0 and infinity over infinity. But we also have a number of other very important examples. For instance, if you see 1 over 0, if you see 1 to the infinity, infinity minus infinity, infinity to the 0, and so on and so forth. Right, so these are all expressions that involve mathematical symbols. The mathematical symbols are in fact defined, but just written down like this, they're not precisely defined. They don't really make sense. For instance, a good example that a friend of mine in the department uses is just take the idea of 1 over 0 and try to rationalize this, figure out what this means. What does it mean to have 1 pizza divided by 0 people? This does not really make sense at all. So the idea here is that if you encounter a term like this, you have to work a little bit harder to actually figure out if it has any mathematical meaning to it. And all of these, as written right here, are not defined, but they're very, very important in applied mathematics because the answers to a given problem in, say, physics or chemistry or any area of engineering application are going to involve the limits of functions. And these things specifically appear in the sense of limits of functions. So what we need to do is figure out a consistent way of evaluating such limits in the case that we have a certain engineering problem and we need to figure out the limit of two functions that is resulting in some indeterminate form. The main tool that we're going to have to evaluate indeterminate forms is going to be what's called L'Hopital's rule. And this is going to be initially stated, right, for these two types of indeterminate forms. So 0 over 0 and infinity over infinity indeterminate forms. However, we're going to see very quickly how to actually extend L'Hopital's rule to more complicated types of indeterminate forms. And it turns out that for all of the different types that you could consider, you can very efficiently and effectively combine and figure out how to algebraically manipulate the problem into 0 over 0 or infinity indeterminate form. And I'll just list one more common indeterminate form that you'll see, which is 0 times infinity right here. So L'Hopital's rule states the following. we have that if f and g are differentiable functions, this means that they're both functions whose derivative exists and is continuous. If g, so the derivative of just g prime of x, is non-zero around some point x naught, and if direct evaluation of the limits in the numerator and the denominator of the fraction f over g are either 0 over 0 or infinity over infinity. So if the limit as x goes to x naught of f which is the same thing as the limit as x goes to x naught of g is 0, or if the limit as x goes to x naught of a function f is the same as the limit as x goes to x naught of a function g is either plus or minus infinity, then we say that the following limit, or the limit as x goes to x naught of the fraction f of x over g of x, so the ratio of the two functions, we say that this limit yields an indeterminate form. And this indeterminate form is either 0 over 0 or an infinity over infinity indeterminate form. Now, remember what we said before, it's not okay to say that it equals 0 over 0 or it equals infinity over infinity, because neither of these two expressions make sense. They're both indeterminate forms. But what L'Hopital's rule says is that we can take the derivative of each one of these two functions in this limit, or the limit of f of x over g of x, will in fact be equal to the limit as x goes to x naught of f prime of x over g prime of x, which is the derivative of f over the derivative of g. And this is the main version of L'Hopital's rule that we'll be using in this course. So there you have it. This is L'Hopital's rule, and what we're going to be doing is seeing how to use this in this lecture, as well as moving on to see how to apply this to more and more advanced types of problems. So the main idea here is the following. Right? What we're saying in this theorem, what this theorem is saying is that assuming these two functions are differentiable and the denominator function is non-zero around the point that we're evaluating the limit at, that either if we have the top of the numerator function is approaching 0, and the bottom, the denominator, is approaching 0. So if we have this, or if we have that the top is approaching positive or negative infinity, and the bottom is approaching positive or negative infinity. So if one of these two things is true, then L'Hopital's rule is saying that f of x over g of x is approaching the same place, or is going to, the same limit as f prime of x over g prime of x. And that's exactly what this theorem is saying. And it's essentially how we use it whenever we're going to directly apply L'Hopital's rule. So this is best seen with examples. So let's just kind of jump into a couple relatively straightforward examples. The first example that we'll consider is the following. Let's look at the limit as x approaches 0 of cosine of x minus 1 divided by x, and see where this limit is going to be. Now, the first thing to notice is that this limit yields an indeterminate form. Because as x goes to 0, the numerator function here, this numerator is cosine of x minus 1. This is our function f of x. As x goes to 0, the numerator here is going to cosine of 0 minus 1, which is 1 minus 1. So the numerator is going to 0, and the denominator is also going to 0 as x goes to 0. The function x is the function g of x, and this is going to 0 as x goes to 0. So this limit yields the indeterminate form 0 over 0. It's really important that you understand that this is not equal to 0 over 0. So you don't want to put an equal sign next to this limit process, because it's not equal to 0 over 0. 0 over 0 is the indeterminate form that is coming from this limiting process right here. And we need to use a nice method, specifically in this case it's going to be L'Hopital's rule, to figure out what the exact limit is. So from L'Hopital's rule, which can be directly applied because the numerator is differentiable, the denominator function x here is differentiable, and the denominator function is non-zero, the derivative of the denominator function is non-zero around the point 0. So from L'Hopital's rule, this means that this is going to be the same thing as the limit as x goes to 0 of the derivative of this numerator function over the derivative of the denominator function. I'll put over on the side here calculation of these two derivatives. Remember from calculus 1 that the derivative of the function cosine of x minus 1, this is going to be equal to, well, the derivative of cosine is negative sine of x, and the derivative of 1 is just 0. Remember the derivative rule that the derivative of a sum or a subtraction is the same thing as the derivative of each term in that sum and subtraction added together. So it'll be derivative of this is negative sine, and the derivative of negative 1 is 0. This is just negative sine of x. And the derivative of the denominator function is just the derivative of x, which is 1. So from L'Hopital's rule, this limit is going to be the same thing as the limit of negative sine of x in the numerator divided by the derivative of this function, which is 1. And because sine of x is a continuous function, this is just going to be equal to negative sine of 0 over 1, which is equal to negative 0 over 1 or 0. So there you have it, correct application of L'Hopital's rule. So this is just a Desmos plot of this function, cosine of x minus 1 over x. And what I wanted to do was really illustrate, what's going on here. So in the red curve that you see right here is the function. And what I want to show is that the limit as we go to 0 of this function is in fact equal to 0. So just kind of verifying our calculations. And to do that, I'll even put a little line on each one of the points from each side. So a line right here, a line right here. And I'll show what happens as the point approaches 0. So as we approach 0 from the left for x, it's at this point right here that it's going up and down, but the limit as we approach 0 is in fact equal to 0. And likewise, the limit from the right is also 0 as you approach. Just one more time, I'll show. As we approach from the right, the limit is approaching 0. And as we approach from the left, the limit is approaching 0. And from calculus 1, you know that means that this limit exists because the limit exists from the left and the limit exists from the right. And this very clearly verifies our previous calculations. This little applet that I've written up here is in Desmos. It's relatively simple to kind of get up and running and just plot functions out and do little tests like this to kind of verify certain results. And I highly recommend it when you're going through and trying to verify some of the work that you've done or you're doing in this class. So let's do another example. We'll consider the limit as x goes to 0 of 5 to the sine of x minus 1 over 3 times x. And we say that this is going to yield a 0 over 0 indeterminate form. This yields a 0 over 0 indeterminate form because as x goes to 0, 5 to the sine 0 minus 1 is 5 to the 0 minus 1, which is just 1 minus 1, or 0. The numerator is going to 0. And the denominator, 3 times x, as x goes to 0, is also going to 0. This is going to yield a 0 over 0 indeterminate form. So in order to do this limit, we need the derivative of the numerator and the derivative of the denominator. This directly is an applicable L'Hopital's rule problem because the derivative of the denominator, derivative of 3 times x is 3, which is non-zero around x equals 0. And both functions are differentiable. So from L'Hopital's rule, this is going to be the same thing as the limit as x approaches 0 of the derivative of the numerator over the derivative of the denominator. The derivative of the denominator is relatively easy to calculate, just 3. But the derivative of the numerator is going to take a little bit of work, and we're going to want to remember some of our basic derivative laws. Specifically, in order to differentiate the function 5 to the sine of x, we're going to need to use the chain rule. And the trick here is using the simplification or substitution u equals sine of x. So this expression right here is the same thing as the x derivative of 5 to the u. And from the multivariable chain rule now, this is not the multivariable chain rule, but the normal chain rule, the single variable chain rule. This is just going to be the u derivative of 5 to the u times the x derivative of u. So this is from Calculus 1, the chain rule. Also from Calculus 1, you want to remember how to differentiate an expression of the form of a constant to the variable that you're differentiating with respect to, or logarithmic differentiation. It's really, really important, and this example really illustrates this. It's important for you to remember all of the derivative rules and the derivative laws from your Calculus 1 class. So this is going to be natural log of the base, natural log of 5, times 5 to the u, and the derivative of u with respect to x, where u is sine of x, this is cosine of x. So the result here is natural log of 5 times cosine of x times 5 to the u, which is 5 to the sine of x. And now that we've done this important work right here, we can continue with our application of L'Hopital's rule. So this derivative is going to be natural log of 5 times cosine of x times 5 to the sine of x, and this is going to be divided by the derivative of the denominator, which is just going to be equal to 3, because the x derivative of 3 times x is just equal to 3. So this is a constant, L of 5 over 3. This is a continuous function, cosine of x, 5 to the sine of x is continuous. So as we go to 0, this just becomes natural log of 5 over 3 times cosine of 0, which is 1, times 5 to the sine of 0, which is 5 to the 0, or 1 as well. So the limit is exactly the natural log of 5 over 3. And this is the result of L'Hopital's rule, or applying L'Hopital's rule to this problem. This example really shows that remembering our derivative laws is essential to correctly implementing L'Hopital's rule and solving a problem like this. So let's see how to change our Desmos file here to directly verify the results of what we've just done. So if I change the function first off to 5 to the power sine of x minus 1 divided by 3 times x. This gives us a nice visualization of our function from before. And I also want to change the value of the limit that we got. In this case, the orange line right here, the correct value that we calculated was ln of 5 over 3, which corresponds to this value along the y-axis right here. And sure enough, as we go through and take the limit from both sides, the limit from the left is this purple point right here. You see that as we approach 0 with x, the value of y is approaching the limiting value, ln of 5 over 3. And likewise, as we approach from the right, which is this blue dot right here, the y value goes up, it goes down, goes up again, and then it converges to the correct limiting value, which is ln of 5 over 3. So there you have it. This rule is very, very successfully determining for us the value of specific functional indeterminate forms in the form of a ratio. For the next example that I'm going to show, I'll show that sometimes we have to apply L'Hopital's rule multiple times to get the correct result. So for example, we're trying to find the limit as t goes to 0, and I'm going to change the variable here a little bit to show that really the variable that you're using for the function does not matter as long as you're consistent. So the limit as t goes to 0 of e to the t minus 1 minus t divided by t squared. This is going to yield a 0 over 0 indeterminate form. It's very, very important that you do not write that this limit equals 0 over 0, because that would be mathematically incorrect. 0 over 0 is an indeterminate form, and as such, it only makes sense in the context of the limit that you're evaluating. This is a 0 over 0 because the numerator goes to e to the 0 minus 1 minus 0, which is 1 minus 1 minus 0, or 0, and the denominator goes to 0 squared, which is also 0. So this is why it yields a 0 over 0 indeterminate form. So in terms of evaluating this, these derivatives are a little bit easier to evaluate than in the previous problem. The derivative of e to the t minus 1 minus t goes to, well, the derivative of e to the t is just e to the t. That's the defining property of the exponential function. The derivative of 1 is 0. And the derivative of t is 1. So the derivative of our numerator function is this, and the derivative of our denominator function is going to be the derivative of t squared, which is 2 times t. Again, we're allowed to do this because both of the numerator functions and the denominator functions are differentiable. And not only that, the derivative of the denominator function is 2t. This is non-zero in the region around the limiting point, which is 0. So 2t is non-zero around t equals 0. So this is why we can apply L'Hopital's rule. Again, we get another, right, this limit right here, again yields an indeterminate form. Because the numerator is going to e to the 0 minus 1, which is 1 minus 1, which is 0, and the denominator again is also going to 0. But have no fear, because we can again apply L'Hopital's rule. So we again take the derivative of the numerator function, which in this case is going to be e to the t minus 0, which I'm not even going to write. The derivative of e to the t is e to the t. The derivative of 1 is 0. Divided by the derivative of the denominator function, which is the derivative of 2 times t, or 2. And this function is a continuous function of t, and therefore this is just going to be going to e to the 0 over 2, or 1/2. And I encourage you to go through and verify this in Desmos. I've shown you how to do it for 2 examples now, so you should be able to go through and open up that the Desmos applet in our course page that I just showed, and verify that for yourself. At this point in the lecture, I want to make an important note. We can also apply L'Hopital's rule to limits at infinity, as well as just limits to any finite x value. And the reasoning for this is the following. This is as the variable x goes to plus or minus infinity. So if we have a limit like this, a limit as x goes to positive infinity, say, where we have a ratio f of x over g of x, and this ratio yields an indeterminate form, this limit can be directly rewritten by applying a helper variable. Say, we'll say tau is equal to 1 over t. Because this is the same as saying that. Right, so if we're considering the limit as, tau is equal to 1 over x. If we let tau equal 1 over x, then the limit as x goes to positive infinity is the same thing as the limit as tau goes to 0 from the right-hand side, from the positive side. So in terms of our functional limit, this becomes the same thing as the limit as tau goes to 0 from the right-hand side of f of 1 over tau over g of 1 over tau. Right, this is basically using the helper variable to rewrite our limit as x goes to infinity in terms of a limit where L'Hopital's rule will in fact apply. And then we can apply L'Hopital's rule to this expression right here to get this is the same thing as the limit as tau goes to 0, the positive of the derivative of this expression with respect to tau, which by the chain rule will be f prime of 1 over tau times the derivative of 1 over tau, which is negative 1 over tau squared, divided by the derivative of the denominator with respect to tau, which is g prime of 1 over tau times negative 1 over tau squared. So you see that the negative 1 over tau squared cancel out. And what we're left with is the limit as tau goes to 0 from the positive of f prime of 1 over tau over g prime of 1 over tau, which is the same thing as the limit as x goes to positive infinity of f prime of x over g prime of x. So this quick justification shows why we can also evaluate limits as x goes to infinity and use L'Hopital's rule directly. Right? We don't even have to take this step right here, this intermediate step. Sometimes it does help to do, but we don't need to do this. This is just a good enough verification for us that L'Hopital's rule can directly be applied. So let's see some examples of this in practice. Let's look at the limit as x goes to infinity of the natural log of t, or natural log of x over x squared. This yields an infinity over infinity indeterminate form. Because the limit of the natural log function goes to positive infinity as x goes to infinity, and the limit of x squared also goes to positive infinity as x goes to infinity. So this yields an infinity over infinity indeterminate form. So directly applying L'Hopital's rule to this problem, and you've seen I've done this in a number of different examples, but whenever I apply L'Hopital's rule, I'll write the LHO symbol for L'Hopital over the equal sign to denote that I've applied L'Hopital's rule. It's really the most convenient way, I think, of indicating that you've applied L'Hopital's rule to get from one side of the equality to the next. But the derivative of ln of x is 1 over x, and the derivative of x squared is 2 times x. So this simplifies then to the limit as x goes to infinity of 1 over 2 times x squared. And this has a limit of 0. So the limiting value of this function is 0. And we can actually use this to directly say then the natural log function grows to infinity at a slower rate than the function x squared. X squared is dominating the natural log function. It grows faster than the natural log function. And this is a nice way of interpreting problems like this, right? When you basically have that the numerator function here is going to infinity and the denominator function is going to infinity. If their limit is going to 0, or really any finite value, you can say in some sense that the denominator function is growing at a faster rate than the numerator function. So the limit actually has a geometric meaning and a physical meaning in terms of the output of these functions. For another example, we can look at the limit as x goes to infinity of t squared over e to the x. This also yields an infinity over infinity indeterminate form, and if you evaluate what this limit is from L'Hopital's rule, this is going to end up being the same thing as the limit as x goes to infinity. Oops, I just realized I need to put a t here. I should have put an x there. This is going to be the limit as x goes to infinity of 2x over e to the x. because the derivative of x squared is 2x, and the derivative of e to the x is e to the x. This is another good example where we're going to need to do another application of L'Hopital's rule, because this 2x over e to the x as x goes to infinity is another infinity over infinity indeterminate form. Right? This yields an infinity over infinity indeterminate form. So we need to do another application of L'Hopital's rule. This gets rid of the 2, because derivative of 2 times x is just 2, and the derivative of e to the x is just e to the x. And so this limit is going to be the same thing as 0, because e to the x is going to positive infinity as x goes to infinity, and therefore 2 over this very large value as x gets larger and larger and larger, and therefore this limit is going to be equal to 0. Because the limit of the denominator is going to infinity. And we can also use this to say that the function e to the x grows faster than the function x squared. They're both going to infinity, but e to the x as a function is growing much, much faster than x squared. This is actually a property, a very general property that we've shown using an example for relating the exponential to polynomial functions. The exponential function grows faster than any polynomial function, and any polynomial function grows faster than the natural log function. So this is a very actually important property in many, many different areas. One area would be computer science, but there are almost infinitely many areas of applications that you can think of to this idea. It's this whole idea of order of growth, or how fast a given function is growing relative to another function. It's very, very useful in computer science, specifically to orders of growth of various functions, and the application is to algorithm runtimes. This is a super, super big application in computer science, and I can talk more about that if you're interested in that a little bit later on. But I want to end the lecture today with a very important example and a very important thing to know. L'Hopital's rule does not always apply. Right? I don't want you to always see a fraction and immediately apply L'Hopital's rule to it. And I'm going to put 2 double lines here to really emphasize this point. This is a very common mistake that introductory students make. So if I were to write, say, the limit as t goes to 0 of t plus 5 over t plus 4, right? We can't apply L'Hopital's rule here. So cannot. We don't need to, right? It's overkill, and not only is it overkill, but it's mathematically wrong, because both the numerator and denominator limits exist and they're non-zero, right? In order to apply L'Hopital's rule, we need to have a 0 over 0 indeterminate form or an infinity over infinity indeterminate form. So for this limit is just going to be exactly equal to 0 plus 5 over 0 plus 4, or 5/4. Note that if you were to try to apply L'Hopital's rule here, you would end up getting 1, or I should say t over t, the limit of t over t, which is 1, which is the wrong answer. It's the incorrect answer. It's not correct to apply L'Hopital's rule here in this situation, because the limit does not result in a 0 over 0 or infinity over infinity indeterminate form. So because the limit does not yield an indeterminate form, you cannot apply L'Hopital's rule. This is a very important point and something that I really wanted to point out with this simple example at the very end of the lecture, because I want you to be very, very careful with this. So for the next lecture, we'll discuss more complicated indeterminate forms, so slightly more complicated indeterminate forms of the form 0 times infinity. We'll start off with that type of indeterminate form, and then quickly move into even more complicated types of indeterminate forms. So we'll work with 0 times infinity indeterminate forms, 1 to the infinity indeterminate forms, infinity minus infinity indeterminate forms, and some more complicated examples, and see how to deal with these types of indeterminate forms. But thank you very much for tuning in. I hope you had a fantastic day today.